Paris in the...
In an earlier video, the one about apples, we ran into the Taylor series, and it told us that functions like the sine wave could be written as a power series, term after term after term to infinity, and that got me thinking. If that's true about the sine wave, then what kinds of functions could we write with a series of sine waves, or sines and cosines? We could make any function, and if it could be anything, then it might also be Paris. So the challenge for these videos is to make the Paris skyline function out of sines and cosines, and here's the big payoff. This took dozens of hours of work, and it's not really that impressive. But the blue wave does match up with Paris, kinda, and I promise it's really made of sines and cosines, you'll see that. But we already knew that. We already knew that complicated math formulas plus computer programs give cool patterns. This blue squiggle was not my motivation for all this work. This was his videos on epicycles, circles on circles. These are the cool patterns I want to explain, or halfway explain. As impressive as these epicycle drawings are, they do require animation and programming skills that I just don't have. My goal is to use math to get us halfway there, the Fourier series, and computers, but only simple stuff, only simple spreadsheets, and only paint. And we'll still get a mathematical result that matches up with any picture of my choice. Let's do it. Get a picture, put it in Paint or Google Drawing or something simple like that, make an outline. This is our function. This is a major limitation, because being a function, each x value can only have one and only one y value. Boo. This is the brute force method. Choose how many evenly spaced x values you want. I'll take 500, and then get a y value for each x, which takes a while. Then put these values into a spreadsheet, and here's a tip. Instead of writing out each number, type in the equation b7 equals b6 plus 1. Then fill down. Still, that's a lot of y values. Maybe we should be smarter about the points we choose. Let's take these 15 line segments. Here's one of them, from point 1 to point 2. Find the slope, and y equals mx plus b will give you the y value for any x in this range. Wait a minute, what's b? That's b. And here is the outline of Paris in a manageable 15 linear equations. And here they are in a spreadsheet. The x values from one point to the next, from here to there. A calculation for m, and for b, and for y. Now graph x and y, and there you go. Not great, but pretty good. And this is the outline I will build with waves. How? With this big equation, the Fourier series, and it will get worse in a minute. But this is our ticket. Find a0 and a1 cosine pi x over L, and b1 sine pi x over L, then the n equals 2 terms, a2 cosine 2 pi x over L, b2 sine 2 pi x over L, then the n equals 3, and n equals 4, and 5, and on, and each an and each bn term changes every time there's a new n, and this also changes, and here is the big news. See, if you look at that big long equation, all the x's are inside the cosine and the sine functions. X was a position, and now it has something to do with an angle. X was transformed. More on that later. First, who are these guys? This, that, and the other thing. It's not quite as bad as it looks. You'll get used to these guys in the next couple of videos. You will get used to them, I promise. To review, our plan is 1. Get information about the picture. 2. Find the a0, an, and bn terms. 3. Fit this data into a spreadsheet. 4. Draw out a squiggly line. 5. Get something to eat. But before testing out this equation, let's focus on just one term. What is L? Well, it's related to the domain, the x values. X, of course, goes on and on and on, but by convention, the part that repeats can be found from 0 to 2L, or from negative L to L, when that's more convenient. Lots of square waves, but others too, and yep, my equation will graph not one, but an infinite series of Parises. Sometimes you'll see x graphed from 0 to 2 pi, okay, a full cycle. Sometimes from 0 to t, the period. We could think of x as changing constantly in time, or just as time. And that means angular velocity, omega, would be pi over L, which is also part of our sine term. And each new integer n clicks up our angular velocity like standing waves. Each new harmonic is a multiple of a fundamental frequency. No intermediate frequencies, no intermediate wavelengths will work. Just this and that all the way to Paris. With this wave and this one, they work. One is twice as long as the next, but these two waves are not allowed. Fourier will not allow it, which is a little bit insulting considering that he will allow an infinite number of frequencies, just not this one. And you can't do that. I mean, you could if you were allowed to add in another term, but Fourier won't allow it. He will, however, allow you to change the amplitudes. But wait, all these sine waves average out to 0, so how can your line get off the ground? Well, good question. That's what A naught does. And when you add all these Fourier series together, you get those beautiful epicycles. Almost. Notice some are clockwise and some are counterclockwise, some faster and some slower, but all are, trust me, integer multiples of some fundamental angular speed. These epicycles come from rotations in the complex, in the real and imaginary plane, which, according to that Apple video, is related to sines and cosines. Behold, the complex Fourier series, but we'll stick to sines and cosines, and Paris, and line segments, and getting even more simplified. Careful! Only one y value for each x. Ignore those segments. Then Fourier it up. This is a simplified version of the other series. Half the number of line segments and n equals 1 through n equals 5, not 1 through 7. And here's an even simpler version of the skyline. Just two triangles. But with help from this website, we can make our own crude epicycle map. Not terrible, I guess. But again, this is different from what we're doing. This is a closed loop. Rotations in the complex plane. Our sines and cosines are, of course, connected to circles, but in a simpler way. Just up and down. Again, think about the x-axis as time. We want a graph that just goes up and down fast, and then up and down more slowly. Epicycles can do that. Epicycles can do that. Sines and cosines can do that. Remember the square wave? Well, this is what we're going to get to in the next video. I mean, I won't be able to do these animations because I can't do the animations, but in a spreadsheet type sine and cosine way, we'll build up to this in part 2.